today's program, the keynote address. It is a great honor to introduce to our engineering and high voltage applications. He is currently serving as a professor at our NIT Andhra Pradesh. Dr. Srikanth sir completed his PhD from Indian Institution of Bhubaneswar in the area of high voltage applications from pollution control and holds an MTech from Indian Institution of Roorkee. He has more than 13 years of teaching experience along with valuable industrial exposure in the power distribution system and substation. His research interest includes non-thermal plasma applications, renewable energy system, machine learning applications in electrical engineering and power system. Dr. Srikanth sir has published numerous research papers in reputed international journals and conferences, holding multiple patents, and has been associated with several sponsored research projects funded by prestigious organizations. He is also an acting member of professional bodies such as IEEE and the Institution of Engineering, India, and has delivered expert lectures and organized several academics and research activities at the national and international level. We are truly honored to have such a distinguished personality among us today. Let us extend a warm welcome to Dr. A. Srikanth sir for his keynote address.
Thank you for the introduction speech. Am I audible? Okay. Seems like it is AI generated. Please remove several numerous like those words. Okay. Yeah. Is it ready? Yeah. మొబైల్ లేదు పర్సన్ వ్యాలెట్ ఉంది పర్లేదా Hello, am I audible? Yeah. Once again, very good morning. Shall we start? Yeah. So today I am going to give Physics or chemistry topic, but we have enough scope for research for the electrical engineers also in this area. That is what we are going to see today. So, as I told you, you can see the left hand side we have the familiar high voltage area equipment, sphere gaps, insulation testers and all, dielectric tests and all we can do in this area. That is very familiar to electrical engineers, but the other side we have non-thermal plasma and its applications where we need very limited equipment components and all. Only tabletop equipment is sufficient, laboratory scale. You can see the gas cylinders, a few gas cylinders, and the one you can see here at the bottom. Yeah, here. These are the non-thermal plasma reactors. A small glass tubes of 1.5 centimeter diameter. So, with the minimal equipment itself, we can run this lab. If you are interested, you can enter into this area. You can see the applications. Yeah. What is plasma? First, let me say what is plasma. You might have heard about 3 states of the matter. What are they? Solid, liquid, gas, isn't it? So, this is considered to be the 4th state of matter, plasma, nothing but ionized gas. Okay. So, here the thing is that we generate this plasma where the electrons will be having higher temperatures compared to the other molecules. I will show you one picture here. I will show you how to generate plasma, but you can see the applications of NTP, non-thermal plasma, before seeing how to generate it. It has so many applications in wide range of areas. Here I can say I can use so many such keywords, because you can see it is expanding in food processing, agriculture, environmental applications, then biomedical applications. Isn't it wide range of applications, aren't they? So, for example, in environmental area, we have water treatment, water or wastewater treatment we can do, and diesel exhaust pollution control also we can do. Here, in this area only I have done my PhD work, diesel exhaust pollution control using non-thermal plasma. And it has so many other areas, like you see nowadays in India the focus is on hydrogen generation. So, you can use non-thermal plasma for hydrogen generation also. There are papers. Then electrocatalysts are there, photocatalysts, such kind of things are there for surface decontamination, sterilization and all. In biomedical also we have dermatology related applications, and then cancer treatment also you can do using non-thermal plasma. So, and agriculture also you can see, like we normally use water for making the plants grow. When we use plasma treated water for agriculture, the studies say that the growth in plants is more. Like seed treatment also another way of applying non-thermal plasma here. Seeds, before going for seeding itself, we can treat them using plasma, and then we proceed for germination. Then the growth of the plant will be somewhat higher compared to the normal procedure. So, such applications, wide range of applications are there for non-thermal plasma. Let us see how to generate this non-thermal plasma. So, this is a simple glass tube, as I told you earlier. Here we have the diameter is mentioned, yeah, it is mentioned here. Just an example, it is not like a standard diameter or something. You can see here diameter is 1.8 centimeter in the top, and bottom here I think it is 1.2 or something, or inner and outer diameters are also, yeah, for dielectric cube inner diameter is 1.4 centimeter, outer diameter is 1.6 centimeters. This one is for silicon stopper. This silicon stopper is used to hold this electrode. In the center, concentrically, one electrode is placed. Yeah, concentrically one electrode is placed. So that electrode is held by this silicon stopper. Then this is the pathway for gas. One carrier gas we need to send through the tube. That is, for example, argon. Argon gas we can send from this inlet, and then when we are applying high voltage to this inner electrode, the electric field intensity inside the tube will be very high when we are applying high voltage, and the you can see on surface of this tube we have a ground electrode also. Aluminum foil we need to wrap around the tube, and it need to be grounded. Then the medium between this high voltage electrode and ground electrode is nothing but the glass tube wall of the glass tube. So that wall itself will act as a dielectric barrier between this high voltage and ground electrodes, and the barrier discharge takes place here, due to which so many chemical reactions will take place inside the tube, and then the ionization of the gas happens, and it will come in the form of plasma jet from the nozzle. At the bottom we have a nozzle. From here the gas, ionized gas will come in the form of plasma jet. It is in violet color, and some hissing noise will also come. Like corona discharge is known phenomena for you being electrical engineers. What is corona discharge? Air around the conductor when it is high voltage. When it is high voltage, then only, isn't it? Air around the conductor gets ionized. There also same violet color discharged, you can see, you can visualize it, and some power loss, active power loss also will take place to the air surrounding the conductor. So same phenomena here we are using, and not only here, you might have known about the electrostatic precipitator. In thermal power plants we have it for pollution control, isn't it? What is the phenomena there? Electrostatic precipitator. We place negative electrodes, and we place like the walls of the electrostatic precipitator are charged, and the gas sent through the medium room, a big room, let us say. So the gas itself is charged, and the negative particles will be attracted on the walls of the electrostatic precipitator. Later on you need to scrub it, right? So such technology we have. So this is what we are going to talk about in this presentation, and the research gaps we have. As I told you, it is a high voltage technique. So development of scalable pulsed power supplies in the laboratory, it is one of the major research area where there is scope for electrical engineers. Plasma catalyst synergy mechanisms, it is like synergetic with catalyst, means catalysts are the most famous techniques we have for majority of the applications. When we combine plasma and a catalyst, then the synergetic effect we can study. Then diagnostics of reactive spaces quantification, these things are mostly chemical people do. Then energy efficiency optimization strategies, again we can concentrate on this area being electrical engineers. Then integration with hybrid treatment processes also we can do. The constraints we have are listed here. You can say challenges, they are the challenges in this area. For example, in diesel engines, if you see the optimum integration with the existing techniques is a constraint, and then the use of simulation tools is another constraint. Like in electrical engineering, we have MATLAB simulation or PSpice. So these things are already well developed, and you can use them for simulation works. Mostly BTech students, UG students, PG students, they use MATLAB simulation. we need to use console multiphysics in this area in high voltage or non-thermal plasma or dielectrics and insulation, these areas we need to use console multiphysics. So there is a lot of scope, research gap to utilize these simulation tools. Then large scale application is another constraint. Small scale you can do, like as I have shown you, the basic methodology we apply in this non-thermal plasma, as I have shown you, the reactor is of 1.5 centimeter diameter. How much time it takes to treat a bowl of water using this reactor? Let us say we are applying this technique for water treatment. What we need to do, we need to place a bowl of water under this plasma. We need to expose this water to the plasma jet, then frequently we need to mix it, because this is the treatment is happening at surface level basically. Then we need to mix it, then the water gets treated in, let us say, 5 minutes, a bowl of water. Then in large scale if you need to do, then how much time it takes, you can imagine. And the major constraint is that why a small dielectric tube we are taking, why not a bigger one? Why not a bigger one with a large electrode, like a huge electrode of a higher diameter? Why? What is the constraint in that? You might have learned in EMF E is equal to V by L, isn't it? Am I correct? Yeah. So this electric field intensity, it decreases with increase in length. So the diameter, if it is increasing, simultaneously you need to increase the voltage also. Otherwise you cannot create that much intense electric field environment inside the tube. So the tube diameter randomly you cannot increase, right? So the tube diameter has some limitations, and the voltage also, it has some limitations. More than 20 kV or 30 kV if you want to apply for generation of plasma, then insulation problems are there. As you might have learnt in basic electrical engineering, that the insulation requirement depends on voltage level. Current carrying capacity, it decides diameter of the conductor, isn't it? Yeah. So same here, insulation problems will come with higher voltages. So these kind of limitations we have. That's why large scale application is a challenge in this area, and energy efficiency, of course, anyway. Then scalability, catalyst integration, these are also some of the challenges we have. And nowadays food processing also, we are using this technique, non-thermal plasma, and the initial investment is higher in such areas, emerging areas where we are employing this technique. So in biomedical applications also, it is in starting stage. It is in laboratory scale, you can say. In real time applications, if you want to apply this technique, then a lot of work you need to do, research work. Then design constraints are there, then the energy efficiency, thermal management, these are all issues. Compact circuit design, another issue. Like high voltage, majority of the people, like from physics background or chemistry background, they are doing in this area research, non-thermal plasma. What they are doing is they are purchasing a high voltage test set, a company manufactured high voltage test set they are purchasing, let us say 20 kV or 30 kV. As I have shown you in the picture, it occupies a table, right? So in real time application, let us say you want to use it for water treatment and you need to sell a unit. There also you need high voltage. How can you generate high voltage in that application? you want to release a product, water treatment product, then it is a constraint, isn't it? High voltage generation equipment are larger than for small scale applications, small products if you want to build, then it is difficult for you to generate. So such research works you can do, like in our in my PhD area, when I was using this technique for diesel exhaust pollution control, we generated high voltage from battery, 12 volts battery. From 12 volts battery, we generated 20 kV high voltage. The problem is that, okay, the advantage is that we need not to have much current. Current value can be in milliamperes itself. So power is not an issue for us. Power 10 watts, 15 watts, that is also sufficient for us. Because the reactor, it is treated as a capacitive load. Okay. So power, it is not an issue. So from battery, 12 volts battery itself we can generate, we can just step up the voltage level. Current decreases, when voltage increases, current decreases, that is not an issue for us. But still there is scope for research in this area. Then you can explore such applications. Of course, as I told you, real-time diesel exhaust treatment, I mean, when I did my PhD, diesel exhaust treatment was like they used to apply non-thermal plasma for diesel exhaust treatment in laboratory scale for last 20-30 years. They are doing in laboratory scale only. Real time, no studies are reported. What I mean to say, there are some constraints when you are bringing it to real time. The major constraint is that the flow rate, the exhaust here in diesel exhaust treatment, I will show you the picture later. We send the exhaust from one side and it will be released from the other side of the reactor. Meanwhile, it has to get treated. So the way the flow rate dominates the treatment. If the flow rate is more, then it will have less residence time inside the reactor, and the treatment time is less, means efficiency is less, right. So real time exhaust treatment, the flow rate is not in our control. For example, there is a diesel car, it is releasing some exhaust, emitting some pollutants. So you cannot control it, control the flow rate. Otherwise, if you can use a tank, a compressor, and you can store the exhaust and release, so that is an issue again. Whenever if it is uncontrolled, then it may lead to a blast also. So such things are under laboratory scale only now. Real time it has to be done. Then surface decontamination, real time diesel exhaust treatment. You can see selective catalytic reduction is the technique which we are using currently, selective catalytic reduction. So this is a like catalyst, a catalyst will be used to control the NOx. You might have heard the norms, they become stringent day by day. NOx emission need to be controlled, it is almost zero now. In latest BS6 norms, a vehicle, diesel vehicle should not release any NOx, 0.0 ppm or something, some ppm. So to that extent, if he has to control it, people are like Volkswagen scam, you know. Have you heard about Volkswagen scam? So they, like in the laboratory scale, they have their motors are working well. They are releasing very less ppm. Tests are passed. Then when it is coming to the real time, the pollution is more. Right? Such scam, it is notified in, I think in 2020 or 2019 somewhere. So such issues are there. So we can integrate the existing technique along with the non-thermal plasma reactor. You can see a reactor with the zigzag path. As I told you, flow rate is an issue. When you have a zigzag path reactor, this is an idea only on paper. not in practical conditions. When you have a reactor with zigzag path, the exhaust stays inside the reactor for longer time. Do you agree? When the reactor is in zigzag path like this, the exhaust enters here and leaves here, so it is staying more time, for a more time inside the reactor. So residence time increases means treatment efficiency increases. So that is the idea. We can integrate it along with the existing techniques. Then surface decontamination, you can see in this picture there is a reactor. Any object you can place and you can expose it to the jet, plasma jet. Then the surface of the object will be getting treated. You can use XRD or SEM for analysis, morphology analysis you can do. And this is the reactor which we can use for surface decontamination. Then we can use it for water treatment also. You can see in this picture there is a PV panel. As I told you, a battery can be used to step up the voltage level. Similarly, a PV panel can also be used. The voltage getting generated here need to be stepped up, or it can be given to battery and then stepped up using Mazzilli converter and flyback transformer. This is a transformer we use in CRT tubes, small scale applications it has. So you can generate high voltage using this small flyback transformer. The size is this much only. It can be held in hand. Then the reactor you can use for water treatment. And a mug of water can be treated by inserting a electrode here and the surface, if you are wrapping it with aluminum foil, then if you are grounding it, then you can utilize this mug, a glass mug, as a treatment unit, water treatment unit. Then hydrogen generation also from biodigester. From biodigester you can take the biogas and then using catalyst you can separate the hydrogen. It is already being done, but catalyst efficiency can be increased by cascading the non-thermal plasma reactors with it. Then the hydrogen rich gas you can generate. So hydrogen generation can also be done. Yeah, especially for electrical engineers, scope for research, there are 3 topics which I can suggest you. One is compact high voltage sources where you can work, and the other is reactor design or discharge techniques. Then we have machine learning applications also in this area. One by one, let us see briefly. The high voltage sources, compact high voltage sources you can use like the fabricated sources. In laboratory scale only you can use converters and all to step up the voltage level. It can be HVAC or HVDC or pulse or piezoelectric sources can also be used for high voltage generation. Then you can see a model circuit, you can see here resonance, series resonance converter. Most of you might be working in the area of converters, multi-level converters and all. So that is the most famous hot cake area for electrical engineers. So that area also repeated work has been done, 9 level, 13 level inverters and all. So what is the objective in that study? Multi-level inverters. One area I can say the people are trying to reduce the number of switches, number of capacitors, isn't it? So here also this is the basic design of a series resonance converter where you can generate high voltage, but here also there are many switches, capacitors, diodes, so you can reduce the number of components here also. There is scope for research. And compactness is also one of the preferred element in this area, so that also where you can work. this is another circuit. Then the multiple transformers you can add in cascaded manner to get a high voltage. Then reactor designs, the material we are using inside the reactor. For example, electrode, as I told you, it can be placed concentrically inside the glass tube. Then the material we are using it for this electrodes. It can be stainless steel or copper or aluminum. So by changing the material, what is the efficiency of the treatment? How it is getting well? This is a research area. Then sizes and shapes also. People are just changing the shape. Why it should be a cylindrical reactor? Cylindrical electrode. It can be square, it can be pentagon, or it can be something else, a star or a spikes kind of electrode. Then what is the change in the treatment? Efficiency of the treatment. So that way also people are doing research. Discharge techniques, I will show you in the next slide. Yeah, this many types of discharge techniques are available. You can see DBD is the basic discharge technique, dielectric barrier discharge, that I have already shown you a basic structure of the reactor, but it can be a plasma needle type as shown here. A needle is placed inside this reactor. Then we have corona discharge. Corona discharge can also be there. This is said to be coronary discharge. Why? Directly there is an electrode. We are applying high voltage to this electrode, and there is a platform which is grounded, and the subject can be placed here, right, which need to be treated. Then directly it will get exposure to the plasma. This is direct discharge between high voltage electrode and ground electrode. So this is said to be corona discharge. Then we have surface discharge, volume discharge, then microwave discharge, radio frequency plasma. So many types are there. Glow discharge is also there, where we apply DC voltage, DC high voltage. So whether we are applying DC high voltage or AC high voltage or pulse high voltage, that decides the type of discharge it can happen. So you can find so much scope for the research here, for electrical engineers especially. Then we have machine learning applications. Basically, for what purpose we use machine learning? There are two problems which we can solve using machine learning techniques. One is prediction, another is optimization. Optimization techniques or prediction techniques, isn't it? So what is prediction and what is optimization? Prediction of output parameters based on operating parameters. I mean, input parameters are known values. We have a set of output parameters also, but for unknown data, when we know input parameter values, what is the output parameter value? To calculate it or to predict it, we use such machine learning techniques. That they are said to be, the problem is said to be prediction problem. And when we have operating parameters, we need to find the values of operating parameters itself, input parameters itself, for maximum or minimum output. That is said to be optimization problem. For example, I was telling you, okay, one case study also it is included. I will show you that. So machine learning, a part of artificial intelligence. So these are all basics of machine learning. Past experiences are used to predict future results. The case study which I included here is a setup which I used for my PhD thesis, where we have a diesel generator here and a filtering unit. So I will show you next picture. Yeah, this one. This is more clear. You can see the diesel generator which we have, and it is loaded, and we have a filtering unit, and then the plasma reactor here, and the gas coming out from this reactor is given to the gas analyzer, and other side the reactor is powered with a high voltage test set. Then there is a voltage probe, measuring device, and oscilloscope. So this is the basic setup. We have a limited number of components we have. The thing which I have done is that I applied machine learning techniques for prediction of NOx concentration at the outlet. Diesel exhaust is sent through this reactor. It's not working. Yeah, stay there. Yeah, gas is sent through this inlet to the inside this chamber, and it is coming out from the other way. And we are applying high voltage to this electrode placed concentrically. Then the idea is that if NOx is there, NOx means nitrogen oxides. At the outlet, this NOx is dissociated into nitrogen and oxygen. Ideally speaking, practically it will not happen. Practically some higher oxides will also get generated. But ideally speaking, nitrogen oxides will be getting dissociated into nitrogen and oxygen. Nitrogen and oxygen, they are not harmful. Nitrogen oxides, they are harmful. NO and NO2, they are harmful in nature. They cause many diseases for a human, right? So that is the basic idea. Then I formulated it. I have taken some input parameters which affects the NOx treatment. Yeah, this is the reactor real-time picture. These are the parameters which affect the treatment. Then I have chosen a few parameters which can be quantified. For example, electrode shape, it cannot be quantified. Electrode shape, if you are varying, it cannot be quantified. But if it is a size, diameter of the electrode, if you can increase or decrease, it can be quantified. The one which can be quantified and having more effect on the NOx removal, such parameters I have taken as input parameters, and I formulated it as a prediction problem. NOx is predicted, so this is a literature review which I have done, which says, which is done for identifying such parameters, dominating parameters. Then the experimental results we got, then the prediction is started with some basic mathematical methods, dimension analysis and regression techniques, response surface methodology. Then response surface methodology, it is like linear regression only. Only 3 stages I have taken, -1, 0, +1 are the 3 stages, because I varied the voltage from 16 to 26 with a step of 1 volt only, but limited data I have mentioned in this paper using this response surface methodology. I tried to predict it. Then the test data, it is only 10 number of data here in this study. Then I have taken these soft computing based techniques, ANN, fuzzy logic and regression based models. I formulated this problem. Now you can see the step size is 1 and 15 to 26 it is varied. Flow rate is also varied from 4 to 16 LPM. Then the temperature is also varied. Then the discharge gap, electrode diameter decides the discharge gap between high voltage and negative electrode. Then the models starting from ANN, then MLP, multi-layer perceptrons, then fuzzy logic. So such models are used, and the error is keep on reducing. The NOx predicted value is close to the actual value. The fuzzy logic model, here the NOx is 2.53, error, RMSE is 2.53 ppm. Then regression based models are so many types of regression models I have taken. Then the best model I proposed, it is Mattern 3/2 type of regression model. Then I increased the test data also to 50%. Generally training data 70, testing data 30% we take. When we increase the test data, accuracy will reduce. So I want to see the generalized performance of the models. Then I increased the portion of the testing data, percentage of the testing data. Then also it is working. The final ppm, it is 2.17. It started from 10 ppm in my first study, where I published one IEEE transactions with 10 ppm error, and the last study I have done, it is 2.17 ppm for 50% testing data. So such a way, the way I proceeded further in the process of reducing this RMSE has given me good number of papers. Yeah, so then this is our summary. Then we have research scope for ML NTP applications. Not only diesel engine exhaust treatment, that is one case study I presented you, but it can be applied for other techniques also, like I have told you, hydrogen generation it can be done. So here CO2 CH4 ratio, it can be taken as the input parameter along with flow rate, temperature, and the problem is formulated as optimization techniques. It is for maximizing the process and sustainability based metrics. So some parameters are taken as output parameters and they wanted to optimize it. So it is now a optimization problem, not only for prediction, you can use it for optimization also. And here we have another study where supply voltage and frequency are taken as input parameters, and the length of the jet. I told you the jet will come in the form of plasma will come in the form of jet. So how much is the length of this jet? That is the output, right? So that way also they are doing research. So variation in voltage and frequency, how it is affecting the length of the jet. So such studies are also there, and then we have a flow chart given in one of the studies here. These are the references, few references, and thank you for your time. If you have any questions, you can ask.
If anyone has any queries regarding the presentation and all, you may please proceed asking them.
Yeah.
Canal gases can be treated to make the plasma,
Yes.
or there is any limitation?
There is limitation means I don't know, but majority of the people they are using argon, nitrogen, hydrogen, oxygen, helium also. 5 gases I know people are using. They are changing the gas and studying the change of gas on the performance. So such studies are there. Some studies, for some applications argon gas is working fine. For other application nitrogen gas is working well. So like
in pollution, if you are using it like exhaust.
in exhaust treatment, directly exhaust is sent into the reactor.
Many gases will be there.
So majority it is NOx, nitrogen oxides. Along with that CO is there, SO2 is also there, a portion of SO2 is there. But in diesel exhaust, majority of the gas is nitrogen oxides.
Second question.
CO is less. Petrol exhaust, CO is more.
Yes,
Carbon monoxide is more. But diesel exhaust, nitrogen oxides are more.
Thank you, sir. Sir, second one, how to distinguish between quantified and non-quantified parameters? You said few we have to take as quantified.
Yes.
In your PhD work also you have some mention. So
Yeah, I told you, electrode size, it can be quantified, but electrode shape, it cannot be quantified. Like a triangle electrode, a square electrode, how can you distinguish it when you are doing a numerical study? In a numerical study, size how it is affecting, I will tell you. If you are increasing the size of the electrode, discharge gap is reducing. So one of the input parameters I have taken discharge gap.
yes.
So size if it is increasing, discharge gap is reducing. So that way it can be quantified.
Yes, yes.
Shape if you are changing, you cannot estimate the discharge gap. That is the thing. So like that you need to, practically you need to think, you can understand.
Thanks.
Yeah, welcome. Sir?
For solid waste management also?
Solid waste management, you cannot, we cannot use, sir. But the biodigester is normal. So whatever gases it is releasing, those gases can be converted as hydrogen-rich gases.
Okay.
Yeah, that can be done.
Okay. Not directly.
Not directly decomposition or
process.
management we cannot do.
Okay.
Yes, sir. That is there, plasma pyrolysis system is there, but it is not non-thermal, it is thermal plasma,
Okay.
where we generate arc. That is the difference between non-thermal and thermal plasma, cold and hot plasma.
Yes.
Hot plasma generates arc. By the arc, current, its discharge will be more. So consumption of energy is more.
It's like incineration.
Uh,
Is it like incineration?
like incineration.
Yes.
Like incineration. Pyrolysis is there. Incineration only. Pyrolysis, limited oxygen conditions, we use this term, pyrolysis. Plasma pyrolysis is also there, where we use high voltage there also, high current. High voltage, high current sources we use.
Yes.
Yes, sir.
Thank you, sir.
Any further questions?
I told you, no, sir, that photo which, that is taken in my lab only.
Any other students or faculty members who have any more questions to be asked? Thank you so much for your session. I have to mention that your way of explanation was so down to earth. Really, even not only faculty but students, we were, even if I'm not belonging to the department of civil, it was very understandable and it was very nice to listen, and it really motivates as a students, you know, as a teachers, it is their inspiration. They have always been working in the field of research and all. As a student, even we got a thought why we can also think like that, okay, this is what happening. So it really motivates and really, you know, brings the thought to us to think in an innovative way. Thank you so much for your session, sir. Now there is a small tea break session. You may all go and have your refreshments. After the refreshment, we will continue with the technical presentations and all. You may please have your refreshments and you may leave to the, and all the
Electrical Engineering from Indian Institutes of Technology, Hyderabad in 2020. He also entered his MTech in Power Electronics and Drives from Bangalore Institutes of Technology and BTech in Electrical and Electronic Engineering from Pondicherry University. Currently, he is working as a professor in the Department of Electronic Engineering at Sri Vishnu Engineering College for Women. With more than teaching experience and over 6 years of research experience, he has guided many students toward academic excellence. His research areas include artificial intelligence applications in electrical engineering, renewable energy systems, fault detection, optimization techniques, and electrical vehicles. He has published numerous research papers in reputed IEEE Scopus and Web of Science journal and conferences. Dr. Sharad Babu Sir has also received many awards for his outstanding research contributions, including Best Paper Awards at international conferences. He organizes several faculty development programs to encourage innovation and research among students and faculty members. What makes him truly special is not only his academic excellence, but also his dedication to teaching, innovation, and student development. He serves as a role model for young engineers and researchers.
I truly welcome sir to Aditya University. I would like to request you to take the honor of the bouquet. Please, sir. Thank you so much, sir. It really makes it. Moving ahead, let us continue with the technical conference presentation. So here we'll start with Dr. B. Jyoti Madam, paper ID 209, with the content of automated passenger pickup system with identity verification.
Firstly, good morning to all the respected dignitaries, honorable judges, and to everyone present here. I'm Nirakshi from KL University, along with my teammates. We are here to present our research work on the topic automated passenger pickup system with identity verification. So in this slide, there's an image of a girl who is confused about who the actual driver is. So let's imagine a scenario. She booked the cab and she is waiting for her cab and two cabs arrived before her. And she is confused between who the actual driver is because there are two cabs right there. And also current ride-sharing systems rely on OTP-based verification but not driver authentication. Means the passenger here cannot safely approach all the drivers, each and every driver, and ask who the actual driver is that she booked the ride within. In real world scenarios, a fake driver may approach and ask for the OTP and without verification also can proceed the ride. So to solve this problem, we proposed an AI-based autonomous passenger pickup system which identifies passenger verification using face recognition to ensure a safe and secure ride. And this is the literature survey table. Before proposing our solution, we studied different research papers that mainly focus on driver verification, facial recognition, and biometric-based authentication for ride-sharing purposes. Some of them are given here. The first one is biometric driver authentication. The key idea of biometric driver authentication is it uses face and voice recognition for driver verification. And the next one is the face recognition in smart transport. The key idea of it is AI-based facial recognition for identity, and the next one is OTP-based ride verification. It confirms the ride using OTP system. But all of these perform individually, so we identified a key research gap between all the research papers. That is, there is no real-time passenger verification and authentication which makes the passenger feel safe for ensuring a safe ride. So the objectives will be given by my teammate.
Let's see about the objective. The elimination of OTP-based ride-sharing systems. Nowadays, so many people are using ride-sharing and Rapido, Ola like that. In that time, when you book the Rapido, sub example in our university only, when you come out the university at 5:30, so many people are booking the Rapido. At that time, so many users and authorized people are there. In that time, it's very difficult to find them, and sometimes they not lift the mobile. In that time, we use the system passenger identity verification by using phase regression.
So the methodology is, first the user books a ride using any ride-sharing platform. Suppose, for example, existing systems like Ola, Rapido, Uber, and etc. And the vehicle arrives using GPS navigation. And after the vehicle arrives, the vehicle identifies the passenger using face recognition techniques. And the car doors will unlock if the registered passenger matches with the already stored passenger details in the database. The car unlocks the doors based on that. And after that, the car communicates with the passenger itself, like how a driver communicates with the passenger using NLP, natural language processing, for seamless passenger and driver, no, sorry, not driver. It's vehicle and passenger interaction. And the emergency alert system detects abnormal behavior in the cars. The methodology is given in detail here. The user books a ride using any ride-sharing platforms, and the user details are stored in the database along with the passenger image captured at the time of the booking. And the autonomous vehicle arrives using GPS navigation exactly to the passenger's location. And after arriving at the passenger's location, camera performs face recognition at the pickup. And if face matches successfully with the registered image in the database, then only the car gives access into the so that the passenger can board the vehicle. And it also has NLP assistant to ensure seamless interaction between vehicle and the passenger. And if any abnormal behavior is detected, emergency alerts are being made. So coming to the results and discussion, these are OTP-based verification systems. Means we first perform a testing on OTP-based verification systems. We keenly observed what is the research gap in the OTP-based verification system. In the OTP-based verification system, if the OTP entered is wrong, there is a red color buzzer there. And if the OTP entered is correct, there is a green color and access will be granted into the vehicle. And coming to our proposed hardware prototype, it uses Raspberry Pi and camera. So the system performs real-time face recognition at the pickup point. Only if the passenger is verified, the vehicle allows access into the vehicle allows access by unlocking the doors. This eliminates dependency on OTP-based systems, ensures physical identification before leading entry into the vehicle. So the passenger safety is a critical information taken into action here.
The main purpose of this project is to give them more safety for the passengers. The before first to existing system only the system based on the only OTPs. If the OTP is unauthorized person will access it, the whole vehicle will access by the unauthorized persons. Because of this system, the unauthorized persons access the vehicles. Our proposed systems identify the face. If the passenger is booked the vehicle, the passenger face verification is registered in the vehicle. If the vehicle is coming to the pickup point, it checks the passenger face verification. If the registered face and passenger face matches, the vehicle gets the access to it. Now coming to the conclusion. The current ride sharing system use OTP to verify the rate, not real time, the physical identity pickup. Actually, before existing system, the OTP is only trust-based systems. If the OTP is misused, the safety of the passengers are not in safe. The proposed system uses face recognition to verify the passenger at pickup. Overall, the system enhances ride safety by adding a real-time identity verification layers at the pickup. Some references of this project. These are the references of this project. Thank you.
There are any queries regarding the presentations?
Good afternoon, everyone. Your project is very good. Thank you for explaining it. I just have a small doubt. We always not book the vehicles for ourselves, right? We book for someone who's waiting at another location to reach us or something. We have similar situations, right? So what should we do then?
So if we want to close
Actually, in that time, you register the person face only. Okay.
If the face is not available.
Yes.
Yeah.
In that time, you capture that photo in registered place. You give that face only. Okay. Person face only you give that.
Can I explain in Telugu?
Okay, can I explain?
అంటే నేను చెప్పేది ఏంటంటే మనం ఇక్కడ ఉండి వేరే వాళ్ళకి
యాక్చువల్ గా మనం రిజిస్ట్రేషన్ చేసుకున్నప్పుడు మీరు వేరే పర్సన్ కి చేసుకుంటారు కదా రిజిస్ట్రేషన్ వేరే పర్సన్ కి రైట్ అనేది బుక్ చేద్దాం అనుకుంటున్నాం. దట్ టైం లో మీరు ఇచ్చే ఫేస్ ఐడెంటిటీ అనేది ఆ పర్సన్ ఐడెంటిటీ ఫేస్ వాళ్ళు మీ ఫ్రెండ్ ఫేస్ అనేది రిజిస్టర్డ్ దాంట్లో అప్పుడు వెహికల్ అనేది ఆ ఫేస్ ని ఐడెంటిఫై చేసుకుంటాం. అక్కడ ఉన్న పర్సన్ ఫేస్ అంటే అట్ దట్ టైం మీ ఫేస్ ఇవ్వకూడదు, మీ ఫ్రెండ్ ఫేస్ ని అక్కడ రిజిస్టర్ చేసుకోవాలి.
You know Swiggy, right? మీరు స్విగ్గీలో ఫుడ్ వేరే ఒకరికి బుక్ చేస్తారు కదా, అప్పుడు మీరు ఎవరి డీటెయిల్స్ ఇస్తారు?
వాళ్ళ అడ్రస్.
ఇక్కడ సేమ్ అలాగే వాళ్ళ అడ్రస్ బదులు నువ్వు వాళ్ళ ఫోటో ఇస్తావు. లేకపోతే స్విగ్గీలో మనం ఆర్డర్ ప్లేస్ చేసిన తర్వాత వీళ్ళు షేర్ డీటెయిల్స్ ఏ ఆర్డర్ ఇస్ ప్లేస్ ఫర్ యువర్ ఫ్రెండ్ లైక్ షేర్ చేస్తాం కదా ఒక లింక్, అలా మనం ఒక లింక్ పంపి వాళ్ళ ఫేస్ ని క్యాప్చర్ చేయొచ్చు.
అటానమస్ వెహికల్ కదా, హ్యూమన్ ఎన్విరాన్మెంట్ అనేది ఏమి ఉండదు అన్నమాట. ఓన్లీ వెహికల్ ఇట్ సెల్ఫ్ ఇట్ కంట్రోల్ ఇట్ డ్రైవ్స్. ఓకే, అండర్స్టాండ్. థాంక్యూ.
I request if the judges have any questions.
Please go to slide number 5. Can you explain what is NLP?
It's a natural language processing.
Thank you. Okay.
Any more questions, sir? Thank you so much for your...
Thank you, sir.
Now, I would like to invite Dr. P. Balakrishna, paper ID 297, with the title of... Okay. I would like to invite Dr. G. Balakrishna.
G. Ramulu.
Ramulu. Okay. I would like to invite G. Ramulu, paper ID 297, with the title of Presentation Performance of the Modified Submodule Based Modular Multileveler Converter Based on ARM Inductance.
It is requested for the presenters to take 10 minutes, and for the rest of the 5 minutes is for asking questions.
Good morning to everyone. So, I'm Dr. Ramil Ganji. So, my paper is 297. My paper title is Performance of Modified Modular Converter. So, based on ARM inductance. So, this is the presentation. So, first of all, we have to discuss about the introduction of MMC and also challenges in MMC and what are the drawbacks in MMC and what do you have methods are implemented in the literature review and go into the performance of proposed MMC and we have to see the results. So basically, inverters are converting fixed DC to variable AC voltage. Two-layer inverters are implemented in 1971. So in the two-layer inverter, the output voltage is getting number of levels are 2. So that means the more number of harmonics are present in the output voltage. So to reduce the harmonics, large size of filters are required. So, for using large size of filters, the cost of the converter will be increases. So, to overcome the drawback here, multi-layer inverters are implemented in 1980. So, in the multi-layer inverter, the number of levels of the output side can be increased based on the switching components. So, we can see the multi-layer inverters classified as cascade switch inverter, MPC, and flying capacitor multi-layer inverter. So these are the basic structure of various multi-layer inverter. So like NPC, neutral point clamped, flying capacitor and cascade switch inverter. So all inverters also here, some drawbacks are there. So coming to NPC and flying capacitor, suppose any one of the switches is failure, so the entire system will be damaged. So to overcome that here, cascade switch inverters are implemented. But here, the number of levels of the pole voltage can be increased, so number of H pitches. So that means each H pitch require one DC voltage sources. That means the number of DC voltage sources are more for increasing the number of levels at the output side. So to overcome that here, MMC was developed in 2001. So modular multi-layer converter. So this is the basic structure of modular multi-layer converter you can see. So this is 3-phase inverter. So here in each phase, so 2 arms are there, upper and lower arm. So in each arm, number of submodules are contained in cascading form and with the arm inductance. At the same time, the input of the DC voltage, the input of the converter is DC voltage. We can see that this is DC link voltage. So the beauty of this converter is at any instant of time period, only n number of submodules are turned on and this will be connected across the supply voltage. So that means the submodule voltage should be maintained rated value, that means VDC by N. And the advantage of the MMC as compared to the multi-layer inverter. So first one is the modularity, scalability and low density. So modularity means same identical submodules can be used in the MMC. And also scalability. We have to increase in the number of layers, we can easily place in the submodules in each arm. But here, so one of the channels are there. So first one is the submodule capacitor voltage. So due to the switching frequency, and you can see the formula here, del V is nothing but ripple voltage in submodule capacitor voltage. So it will be increases by decreasing the low frequency, that is omega. And over here, by decreasing the size of the film capacitor also, it will be increased. So mainly we have to observe the 2 parameters. So one is when the load frequency decreases, the ripple content will be increased in the submodule capacitor voltage, and also here due to the switching frequency. So due to that, some problems are coming. So like circulating current, common mode voltage, modulation index, and also power losses. So to overcome the drawback, here so many modified topologies are implemented. At the same time, modified pulse width modulations are implemented in the literature review. So these are the papers I have studied. So what I observed from the literature review, So many modified tables are implemented, but it having some drawbacks like, some modified means some additional circuit is implemented in between the upper and lower arm. So due to that here, the components are increases, so further the cost of the converter will be increases. So to work on the drawback here, so I have designed a novel submodule based MMC. So first of all, we are updating the what are the objectives we have to find in this type of converter. So first one is we have to reduce the submodule voltage ripple with the help of arm inductance, and also we have to see the power losses by varying the arm inductance, and also we have to observe find out the formula of arm inductance for the proposed converter. And you can see that this is a modified submodule based converter. So two converters are there. So second one is a conventional MMC and first one is a novel submodule based MMC. So here you can observe the new submodule in the conventional MMC. So only two switches are there connected across the capacitor. But in the proposed submodule capacitor based MMC, here same size of capacitor here also using, but with one additional switch. And here this is the working operation of proposed submodule. So any arm current consists of AC component, DC component. Due to that here sometimes it having positive and sometimes it having negative. So when the arm current is positive, so DI is connected, so like that here the capacitor is charged. And when the arm current is negative, so the capacitor discharging through the same capacitor. And you can see the four working operation here of the proposed submodule. And this is the switching characteristics of proposed submodule. And this is the equivalent circuit diagram of proposed MMC. So you can observe here. So in each arm, so V2 ashta, that is nothing but due to the additional switches, some ripple component is presented which is opposite to the proposed submodule capacitor ripple voltage. So due to that here this can be compensated with the help of additional switch. And these are the parameters I have chosen for developing the proposed submodule, and also here it is simulated using MATLAB. And these are the years, so when I implemented in the MATLAB, so definitely you can observe the proposed MMC. So generally here taking the number of submodules are 2, so that means the number of levels will be 2n plus 1. So that is 2 into 2 plus 1, that is 5 levels are counting. But due to the use of arm inductance is 10 millihenries, I am not getting the output voltage 5 levels. Sometimes it is distorted and sometimes it is getting the 5 levels. And when the arm inductance is I am changing from 10 millihenries to here 3 millihenries, we can observe the output voltage is getting the 5 levels. And also we are observing the BC nothing but submodule voltage, capacitor voltage. It is maintained at relative value with less magnitude. And also I am changing the arm inductance, so from 1 millihenries to 0.1 millihenries. So same output voltage is getting, but the ripple content in the submodule capacitor is increases as compared to the previous one. And also I have calculated power losses at different values of arm inductance. So you can observe here this is the power losses at various of arm inductance. Here the arm inductance is 0.1 millihenries, we are getting the low power losses. So from that I have implemented so many ratings of proposed converters. So finally I have designed the arm inductance. So this is the formula of arm inductance, that is LRM. And capacitor size is already designed based on the previous latest review. So finally I have concluded, so we have to reduce the arm inductance. So we have to choose the arm inductance. So based on the ripple content in the submodule capacitor voltage. This is the reference. Thank you. Any doubts?
Why the inductance value is affecting number of levels?
So no, sir, actually arm inductance acts as a filter. but we have to reduce the size of the filter, but we have to improve the performance. Performance means we can observe the arming reactances, going to the slide. Yeah. So when the arming reactance is 10 milliamperes, we can observe the submodule capacitor voltage. So it does not maintain the rated value. So due to that, it will be affect on the output voltage.
Not on the output voltage, it is affecting the number of levels also. Why it is so?
Due to the modeling mix also, sir. So due to that, modeling mix also increases.
Go to reference slides.
Previous, sir?
References.
Yes, sir.
If you see reference number 12, is it audible?
Yes, sir.
Go to see reference number 12.
Yes, sir.
So compared to that paper, what is the novelty in your work?
Yes, sir. In that paper only they focused on the submodule, modified submodule only. They did not focus on the arming reactance. So generally in that paper they choose in the normal value of the arming reactance. But here I have analyzing the same paper with the different values of arming reactance.
Any further questions by the students? Thank you, sir. Now moving forward for the next participant with the paper ID 175.
Good afternoon to session chairs and all the participants as well as co-presenters. This is Kota Reddy from JNTU. My paper ID is 175 and the title of the paper is Evolution of THD, that is Total Harmonic Distortion in a Interlude Switched Boost Common Ground Multi-Level Inverter. So the main objective is to eliminate the bulk transformer as well as the leakage currents in the transformer. If you are using a transformer, it is, if in a 3-phase we may use a delta connected transformer. So obviously the leakage currents are eliminated. Here the intention is to eliminate the transformer as well as to suppress the leakage currents in a multi-level inverter with the help of interlude as well as switched boost combination. So generally the multi-level inverters produce high power quality with the increase of the number of levels. So if you are to increase the number of levels, obviously we using more number of switches as well as we have different number of topologies with reducer switch topologies as well as to improve the THD, to reduce the THD also. Here we go with a switched boost topology. The intention is to get, we are using a transformerless DC to AC conversion. I mean, we need to integrate the DC source to the grid. So in that, for dynamic voltage change, we are using a switched boost topology. So coming to the literature, what we are concentrate on, so the advanced topologies to improve the number of levels with the reduced switches as well as we are offering the interlude structures with the advantage of the beauty of the interlude structure is we can eliminate the ripples in the input current by interfacing, and in the conventional, and also it is a single stage conversion from DC to AC, it is a grid connection. So inbuilt we had a switched boost and we have a multi-level, that is DC to AC conversion. So which provides a high efficiency by reducing the THD as well as losses in the components. So and from the literature we are identified these the 4 graphs, that is the structure should be a simple topology and it should be offer a low ripple in the input current and provide the continuous input current and minimize the leakage current. So the intention is to eliminate the transformer. So without transformer we are providing a minimum leakage current by the common ground. Our input as well as output are the same common ground, and we can implement that advanced PWM techniques, that may be SHE or we can implement PSPWM, phase shifted pulse width modulation. And so the major objectives are the circuitry. It offers a modular structure. We can extend to the n number of levels, and reduced voltage edge, if you have some n number of components, all the components having the same voltage stress, so that depends upon, that means you can easily replace the components with the equal voltage stress, and common ground feature which eliminates the leakage currents measure, and with the advantage of the interlude, we can get a continuous input current with minimum ripple. So it is the topology of the our proposed circuit. Here we are proposing N channel. Here the descript about the single module QCH bit cell. Each QCH bit cell offers a 3 levels, that is plus VCA, plus and minus VCA with 0. So here the input side we are having a switched inductor. This S1 which is used to boost the input voltage, and so based upon the duty cycle which are giving for the S1A, that is the switch, the output voltage will be boosted up, and based upon the switches in the HQCH bits, that is S2A, S5A, S3A and S4A, we are connecting the capacitor voltage to the grid, and we are connecting actually the intention is to get a bidirectional power flow, but we are using a resistive load only here with RL load to see the performance of the proposed converter. And these 9 levels will produce a plus, actually with the input we are taken as a 120 volts with the duty cycle of some 0.8, the capacitor is charged to the 600 volts, and with the modulus index selected for the H bits, that is QC bit cell, we are choosing as a 0.8 is the modulus index. With that we can get a, in output we are getting a plus or minus 480 into the highest level. With that we can get plus or minus 120 into 4, 120 into 3, 120 into 2, as well 120 is the, these are the positive levels, especially we are having the negative levels too. So here the modulation we are using a phase shifted modulation. So among the 4 switched inductors we are using in the interlude fashion. So each inductor will be switched by a 360 by n, we are 360 by 4. So each inductor will be switched with the angle of 90 degrees, so that the input current will be provided a minimum. In the switched, in the interlude configuration, if you are increasing the number of phases, the ripple in the input current is reduces so much. So we are going further, we are going for the interlude connection. And one more important is the same carrier signal we are using for producing the pulses for the switched inductor as well as H bits, QCH bits. So here we can consider, for that we are considering a DC of the DC is the for switched inductor, and this reference for HQCH bits, and these are the respective pulses of 1 H bits. And this type of bridges I have 4 switches, so 4 H bridges with 90 degrees phase shift in the carrier. And these are the simulation parameter. So we are using MATLAB is the environment for simulating the proposed topology, and these are the parameters. The input voltage we are considering is 120, and the switching frequency is 50 kilohertz, and it is the floating capacitor. The intention is to charge the capacitor, this 15 microhenry capacitor to the 600 volts, and then with the help of the duty ratio we are converting it to the 480. It is the peak level, that is the maximum level. This is the input voltage, and this is the output voltage. We can observe the 9 levels in the output, okay, and this is the current, output current with a very, it is the capacitor voltage. It is oscillating around 600 volts. Actually it is a 608 actually we can observe. And in the output current, because of we are considering a pure RL load, that's why in addition to the RL load we are connecting a series inductor, that's why we are taking a smooth sinusoidal current in the output. And these are the THD performance, but the both voltage and current. Here we are comparing, actually it is a single stage DC to AC conversion. So we are comparing this with the existing conventional 9 level H bits. In the conventional 9 level H bits, we are using a 4 DC sources individually. In that you need to offer a isolation between the 4 sources. Here we are using only 1 source, so that there is no need of any isolation between the sources, among the sources. And the number of switches, if you are using the DC to DC converter as well as conventional H bits, we are using the same number of components, here 20 as well as 20, but thank you. So coming to the results, as compared with the 9 level convention CHB, we are the proposed interlude switched boost common ground interlude multi-level inverter gives a low THD as well as for the voltage as well as current. Okay. Yes, and the major advantage is we can eliminate the isolation, we can eliminate the bulky transformer, as well as we can get the modular structure in the switched boost multi-level inverter, common ground, especially with the common ground we are eliminating the leakage current. So, thank you, sir. So, these are the references.
Moving forward for the questions, sir.
Hardware implementation is in process.
Yes, sir. Cheyan.
That's what I'm saying. In future you will do that?
Yes, sir. Yes, sir. Okay. So, starting we are starting with the single phase.
17% THD is more, no?
Yes, sir. Yes, sir. So, on that we are working on the different topologies to reduce the THD. So, initially from the literature we are identify the structure. With that we are going to the different configuration. With different topologies. We are in the H-bit we can change the modulation. Topologies.
Okay.
Next time we are implementing for the 3-phase 2.
Okay. Thank you.
Thank you.
Thank you, sir. Moving forward to the next participant with the paper ID 997.
Good morning, sir. So, is a paper ID 997. Actually, this is the paper of my student. So, in favor of my students, just I am here to present it. Hello. So, my title of the paper is Multi-Level Inverter with Voltage Boosting Capacity for Renewable Energy Source on the basis of Photovoltaic Application. And this is the overview of my presentation. So, regarding the multi-level, so why we go for the multi-level? Why you are not going for inverter? So, these are two questions will come when you go with the multi-level. So, inverter is nothing but it is a converted DC to AC generally. But if you see that inverter, general inverter, the voltage stress is very high. So, that is dV by dt is very high. That may cause some problem. And one more thing, when the inverter is switching operation, it generates some harmonics. So, if you go for multi-level inverter, these two can be overcome. So that's why we will go the multi-level, and nowadays we see that we have different types of topologies are there in the multi-level. So mainly multi-level increase the operation of high voltage, output voltage, and the level, I can say the harmonics can be reduced, and you can see the smooth waveform of the current when you go to the output voltage. So that's why this is the multi-level inverter is very important as compared to general conventional inverter. So generally if you see that these are the three basic inverters, I can say multi-levels we are having in the one is a neutral point, NPC, FC and HB. So neutral point clapping is there. Here if you see that we have a number of diodes are used here. So if you see that if any switch is off, that means the topology will be failure. And second is a capacitor multi-level inverter. So here if you see that we require, if we go for number of multi-levels, we require the more number of capacitors. So that is one more problem. Okay, sir. So mainly I am going with the main objectives. So here the multi-level is integrated with the photovoltaic system. So here I want to make technical objectives is, so designing the multi-level inverter. For that I am going using the pulse width modulation technique, and we have some boost converter, and we can see the different solar radiation input for the output. Now this is the main block diagram. Now the block diagram consists of here a simple voltage VDC, and we have two capacitors C1, C2 and three diodes D1, D2, D3. This is the main capacity. Now here if you see that, so let me go this one, right. Now here if you see that we are having three switches left side, and we have the HB inverter toward the right side. Main HB inverter is used to output can be AC. When I have two switches, we get AC output. To generate the positive and negative offset, we go the HB converter. So, and we go the phase difference pulse width modulation. Here if you see that we are having the 7 carrier waves. So one reference wave is generated. On the basis of that we are going to do the number of pulses, and this is a switching table for the converters. And these two capacitors C1, C2 is used for charging the and discharging the battery. Now mainly this capacitor is used to maintain the balance voltage. And these are the result discussions. Now we can see the solar radiation. So here 0 to 0. Up to 0.5 we have the radiation is 1000, and after that the radiation is reduced to 500. So then from that, if you see that the current in the PV is having variation, then finally from this graph you can see that the difference voltage and the actual voltage is almost tracking in the system. Now come to the in output voltages. Now here I am going with the 7-level inverter. Now the first one, if you see that the load is getting the R and RL load. So 0 to 0.5 it is the R load, and 0.5 to afterwards we go with the RL load. Now if you see that the current and voltage are almost in the phase, they have this 7-level meter. And the section, then B part, if you see that the value is same, but if you see that the current with the RL load we have smooth variation, and you can see the output voltage and output current there. Now the C traces a capacitor charging and discharging, and the fourth one, if you see that capacitor voltage, current and the source currents. So because of inductor it does not allow the sudden change in current. So that's why when you go to the RL load, we are having a smooth waveform of current. And this is the other waveform. So let me go to the figure 6. Now mainly the modulation induction is the main part in the output voltage. Now this is the modulation as well. When it is 0.9 we get the marginal voltage. So the modulation difference is the ratio of the reference voltage by carrier wave. So if the output voltage always proportional to the modulation index. So and this figure 7 sees the different waveforms for the voltage and currents. And in the A bit, if you see that both are in the phase base, but in the B phase, if you see that because of inductor, we can see some phase differences. We can see there highlight. Now this is the way we can see the phase difference because of inductor load. So my conclusions say that, so definitely, so proposed switching capacitor material inverter is reduce the component, and we have the boost converter. And we use the pulse width modulation where we can reduce the harmonics, and we can have the balanced capacitor voltage can be produced here. And the efficiency of the system is carried almost 97%. And this total work is done in the MATLAB Simulink, sir. And these are some references. Thank you, sir.
There are many papers in this area, no? What is the novelty of your study?
So actually from the topology, just there is small change, and here I am depending on the smoothing of the current. That means mainly the capacitor is going to balance the output voltage. We have two capacitors, that capacitor is going to balance the voltage, sir.
Okay.
Slide 15. So what is the critical difference between switched capacitor and switched inductor?
Switching capacitor.
On first line you see proposed a switched capacitor multi-level inverter.
Yes, sir, switching capacitor.
So switched inductor is there?
No, inductor is not there, sir. Only capacitor. Because capacitor is only the making the voltage balance.
Converters, I think.
On the basis of switches, the capacitor is connected, C1, C2 will be connected, on the basis of voltage can be balanced.
Okay, sir. So are you in a process of doing hardware of this work?
At present, we didn't think, sir, but we will try, sir.
Okay, good. Thank you.
Thank you, sir. Moving forward with the last participant for this morning session, I would like to call up paper ID number 997 participant.
Okay.
Paper, 996.
Myself.
Sorry, sir. Thank you. With this, we wind up. No?
One more paper, sir. This is my second paper, sir. My student paper only, second paper. So, paper ID 996. So, my title of the paper is Design and Simulation of Carrier Pulse Width Modulation Based Capacitor to Support the DVR for a voltage sag and voltage swell for the mitigation of the distribution system. So these are the overview of presentation. Now, main abstract is this paper proposed the carrier pulse width modulation based capacitor supporting dynamic voltage reactor for power quality improvement. So, mainly my project is, okay, sir. So my main object is, so mainly if you see that the power quality issues will occur at the distribution side. So to overcome what is the general power quality, we can say the voltage sag or voltage swell, or I can say unbalance, or some harmonics may be developed. There is a voltage and frequency difference. These are some different power qualities. So here I consider only the three quantities. One is the sag, swell, and harmonics. So these are three quantities. Mainly my objective is the load voltage and current should be smooth. That means it should be sine wave. So whenever distortions occurs. So this is the main block diagram of my topology. Now here's the VSA, VSB, these are three-phase grid voltages. Is directly connected to the grid. Now here if you see that at the point of common coupling, we are having the shunt compensation. That means a multi-level inverter with the capacitor. Here main objective is we are not having any batteries here. Only capacitor is actively charging and discharging. So this is the main topology. And come to the control scheme. Now here if you see that the first one towards the figure 2A. So we are having a three-phase A, B, C line voltages. Now this line voltage is connected DQ axis with low pass filter is kept for removing the oscillations. And from that we come to the line, the phase voltages. So meanwhile if you see that I want to make, I use the phase PLL loop. PLL loop is used to synchronize the frequency and the voltage magnitude of the grid. And second, we have 30 degree phase difference because we are having the line voltage and phase difference, phase voltage is 30 degrees. And second, if you see the 2B top, so here also I am doing I can say the phase angle link, phase angle synchronous with the grid. And second is that I want to find out what is the load voltage differences. Now the load voltage difference is compared to the actual voltages. So by using pulse generator, I am going to switching the operation for the inverter. Now come to the main proposal. This is the main proposal. Now here I introduce only the unbalance, sag, swell, and harmonics. These are three main components. To avoid the power quality issues. So let me see the result in the. Now if you see the first one is the terminal voltage, the grid voltage, and here the load voltage, if you see that it is somewhat smooth as compared to the terminal voltage, and the third one is the DVR, we are having the engine voltage, and fourth one is the load current. Now if you see that there is a sag at between 0.15 seconds to 0.25 of 30%. At that time if you see that the DVR is generating some energy. And whereas in the second case is 0.35 to 0.45, we are having a swell. So definitely we are having a swell of 20%. So that means that the inductor is compensating, the DVR is compensation. That means if you see that here itself, the voltage is reduced, injected, here voltage is received. So this is the case, we can see the load voltage and current are very smooth in the first cases. And second case we will the unbalance. Unbalance is we are having a sag and swell at the same time. So first if it is 0.15 to 0.25, we see that there is sag and swell both are there. So at that time also the DVR is generating energy to make the voltage balance and the current, and 0.35 to 0.4 also we can see the unbalance. And the third slide, next slide, you can see the harmonics are injected. So mainly we see that we are talking about three phase. Three phase means generally the lower harmonics 5th and 7th. So 5th and 7th harmonics are injected here. So at time of 0.16 to 0.24, we can see the grid voltage, we have lot of distortions occur. If the same voltage applied for the load, definitely the power quality should improve. To avoid this one, we are having the DVR injected in the shunt compensation. So here is going to compensate, and finally you can see the smooth voltage and current in the output voltages. And if you see the THD also, it is going to reduce. So generally load current, it is 9.45%, it is reduced to 1.31 as per the IEEE standards 214. So this is a allowed tolerance. And the THD waveforms. And my conclusion is, by this proposal we can use the distribution system. At distribution side we can have some power quality improvement. So even though any distortions occur in the grid side, so definitely that is unbalance or sag or swell. So definitely at the grid voltage and current can be smooth, and you can protect the devices at the load side. These are references. Thank you, sir. Only capacitors, sir, capacitors.
So without batteries, how are you getting the initial voltage?
So actually the capacity is nothing but is simply a battery, sir. Generally it's charge and discharge. Capacity is a storage device. It is a high capacity. It can charge and discharge directly. No need of storage of energy.
Charge and discharge is okay, but initial voltage need to be there, no?
Initial voltage already it is a line.
Charged capacitor.
As a charge capacitor, that it is a line. In the real-time projects, so definitely we have some charging will be there.
Okay.
So thanks, sir.
Nice work. Previous slide. Previous. So I mean, sinusoidal pulse width modulation is already.
Oh, sorry, sir. Is a sensor pulse modulation?
Is a very old technique, no? You can proceed for SVPWM at least.
Yes, sir. Yes, sir. Actually, this is even though sensor pulse is a old technique, but it is having a good efficiency.
Still, that's what I'm saying. Since it is a simulation study,
yes, sir.
You can try for SVPWM.
Okay, sure, sir. Definitely, I will go with the space vector pulse modulation.
Rest of the things are fine.
Okay, thank you, sir. Thank you, sir.
Dr. V. Srinivas Rao sir, HOD of Tripoli, and Professor K.E.S.R. Murthy sir to come onto the dais to felicitate our chief guest of the occasion, Dr. A. Shrikant sir. Please, sir. It is our extreme honor and privilege to have you with us, sir, today in Aditya University. Your presence really helped us a lot. Your knowledge and all really inspired the students and the faculty.
now we would like to conclude and we will like to go for a lunch. For a 1 hour, we will be having a lunch session.